Good afternoon. We are NASA engineers here to discuss our launch day proposals. So my name is Andrew. I am the senior engineer. This is Landon. He is the NASA director. This is Maddox. He is also a fellow engineer. And that's Revan over there. She's our intern. Okay, so we're here today to discuss, as we're going through the safety protocol of our rocket for the scheduled launch next week, we came across some issues. So Maddox is going to discuss those with us.
So I think it's important before we discuss our issues, we go into exactly what an O-ring is and its functionality. So an O-ring is basically just a thin rubber piece that goes in between two pieces that will have running fluid or fumes going through them. And it has a couple of temperature requirements that we have to keep in mind while we're doing our projects. For ours, this specific O-ring has a temperature limit of 55 degrees. And if we run below 55 degrees Fahrenheit, we start to run into issues. For this one specifically, it starts to get more and more stiff until the point of complete rigidity. And after that, it can fail quite a bit. So we have to keep that in mind as we're designing our rocket.
Yeah, so very defining the problem here, we have an O-ring, which we discovered in our testing that if the temperature of the O-ring is less than 55 degrees Fahrenheit, then that means failure for the system, because that O-ring will become brittle and it will break, and that will allow the fluid to get out and catastrophic failure of our rocket. However, the temperature of the launch day, as projected by the weather forecast, is going to be equal to 60 degrees. So that is greater than 55. However, there is a margin of error within plus or minus 8 degrees Fahrenheit of predictability that we just can't tell. And so Landon here is going to get into more specifics of whether or not we should launch.
Also, one thing you have to think about for the temperature of the launch is as you go higher into the atmosphere, it gets colder because of the pressure difference. And so that will reduce the temperature is one reason why we have to come up with other solutions on how we can keep this O-ring a little bit higher temperature. Some solutions that I had thought about were using better materials. Historically, we've used asbestos, which has a little bit of a harder time with lower temperatures. And we can use one called silicone rubber, which is good from negative 100 degrees Celsius to 230 degrees Celsius. And that would just cover a lot more range of temperatures for us. One more thing we can do is add multiple of those O-rings. So instead of just one, two, maybe even three. That's what the Challenger has done in the past. That's another example of something that we looked at. It's a rocket that failed for this exact reason. The O-rings were not sufficient and it broke and caused the whole system to fail, just as Andrew here was explaining.
Another thing to consider though is the fact that our O-rings, they're protected by the outside of the rocket. They're not going to be exposed to these outside temperatures. So we don't need to worry so much about when it's in the atmosphere as it's ascending. It's more atmospheric temperature at the time of the launch and a little bit after. Because after that point, the liquid and fumes inside the rocket is actually going to raise the temperature of those O-rings. So we don't need to worry about that as much.
I agree with your statement, but also you have to think about as you go into the atmosphere, the rate at which the temperature is increasing from the jet fuel being burned, for example. So I agree with that, but I think that's more applicable in space actually, rather than in the atmosphere. Okay. Which is why I agree with the insulation, and that will help us, but also we have another problem solution, which is O-ring heaters. They're little electric heaters that we can put around the O-rings, like through the pipes, through the insulation, specifically around the O-rings, designed to keep them in the elastic range and not becoming brittle.
How about we write our solutions on the board for the audience to see, so they can see all the bullet points that we just discussed.
Alright, I'll do heaters for O-rings. Then we have multiple O-rings in case of failure. We have other ones backing it up, and we also have better materials, which would be silicone rubber. This pen isn't great. But those are some solutions I came up with for this problem. Sorry.
So if we choose to pursue these better solutions and try to mitigate the risk of an O-ring failure, that does come with some costs. It's not just going to be something we can just go replace right now. We're going to have to get into the system and do that. So Revin, our intern, has been doing some research of his own, and he's going to try to discuss that with us.
For sure. So we have two major options here, and that's just going to be launch with these conditions or delay the launch and fix it with these solutions here. And looking at these two solutions, I think that one is the clear option to choose here, and that would be to delay the launch and do these adjustments to the O-rings, one of the few, whatever works the best, because of two major things. And one, it would be cost, and two, it would be like the ethics behind it. So launching right now with these conditions, especially with that plus or minus 8, we really aren't going to know for sure if these O-rings will drop below 55 degrees Fahrenheit. And what that will do is catastrophic failure. The rocket will blow up, we would lose lives, and that's probably the worst possible thing we can have happen during a launch. So the best thing we would do is delay the launch and add these things on here. Now doing that would obviously come at a cost. It would come at a cost of overtime for the workers, like everything having to do with making it better and like having to push back all of our plans. But on the flip side, having a rocket be totally destroyed will cost a lot more, and we would also lose the lives of the astronauts that have been training for this mission for a long time here. So delaying the launch is clearly the best option in this case, especially because of this close range here. So that would definitely be the best thing we should do, looking at all the data we have here. Anything else you guys want to add on to that, or you think that's the best solution?
Can you write down those costs, the opportunity costs of launching and the opportunity costs of delaying it?
Okay. Yeah.
I think, so one solution you're coming up with is delaying the launch. Like for example, if it was predicted to be 60 degrees, but it was 50, or like, let's say bad weather rolled in, also dropping the temperature.
Exactly. We're never going to know. Temperature, obviously, we can get a pretty good guess nowadays, but
Weather's unpredictable.
it's unpredictable. Even if it was 60 degrees, and let's say like 5 minutes before launch, a breeze blew in, it dropped 3 degrees, something happened in the rocket, it dropped below that certain degree. This close range is way too close to be trying to risk it and still launch the rocket, you know?
It'd be better to wait for like a 70-degree sunny day a week later, you know.
A question I had is, does delaying this like launch time, would that lose any money as well?
Definitely, yes. So like I said before, pushing it back would cost more for like paying certain people to work more on this, as well as adding this onto here so that we don't run into the same problem again. But again, that cost of adding these and delaying the launch would be way outweighed by the fact that if we did launch in these conditions and it was a failure, we would lose all of the stuff we already worked on before in the past instead of just adding on stuff to it. So we would have a failure launch with losing lives while having to start from point zero again to make it all over, which would be probably the worst thing that can happen.
And the exponential, like, costless price of losing lives, which I think is just so significantly higher that you can't even put a price tag on a human life. And so, I mean, sure, it might cost a few $1 million, which is no small sum of money, to delay the launch and try to fix these problems. However, if we do launch and the rocket just catastrophic failure, we're losing a $1 billion rocket, we're losing human lives, bad brand reputation, we're going to get a lot of bad media, which we just do not want. And so I think even though people may be upset that we delay the launch, in the end, it's not going to be nearly as significant as if we launched and it failed.
And it's not just about the cost of a failure, it's more about going into how we're all Christians, and the value of a human life can't even be compared to what money costs. So I think just that by itself should tell us that we should delay and wait for safer conditions and safer installations of better O-rings, multiple O-rings, that kind of stuff.
I agree. And piggybacking off that, the Bible says the body is a temple of the Lord. So I mean, we want to do everything we can to keep that temple holy, keep it intact.
As well, it says love your neighbor, and I mean those astronauts in the rocket are going to be our neighbors, and so they may not have the technical knowledge of how the rocket works, and they're trusting us to ensure their safety. And so, as the engineers that are entrusted with their lives, we want to be good stewards of that as well, which is another biblical principle. And so, we want to make sure this is 100% safe and that we can get them back safely to their families.
All right. I think that is our kind of review on this situation of our O-rings having a certain failure temperature and the temperature of the outside. I think we've all kind of agreed that delaying the launch and fixing some certain major flaws in the O-rings for a better launch in the future is better than risking that launch and risking everything being lost in the process.
Don't
Thank you.
launch.
Don't
Thank
launch.
you.